Hi everyone, welcome to Rendering Engine Architecture Conference 2025. Today we will present architectural challenges and decisions related to global illumination, ray tracing, and character creator developed for Dragon Age the Veilguard. First, we will cover the challenges around our probe baking system and decisions made around team size and asset constraints. Next, we will share implementation choices taken for ray tracing, considering the limitation of already existing ray tracing tech with the additional requirement of supporting latest GPUs. Lastly, we will go over our character creator tool focusing on architecture and implementation decisions required for shipping the game at highest quality and performance. Dragon Age the Veilguard is set in fantasy world full of magical effects in vibrant indoor and outdoor environments. Players create and customize their own character and work with a group of followers to explore and save the world from power-hungry deceptive gods. The game was launched for PC, PS5, Xbox Series X, and S in October 2024. It was developed using Frostbite engine, which included world editor, appearance editor, and lighting and rendering pipelines. We had a small content team of 15 to 20 developers working on the environments and 5 rendering engineers on the graphics team. Now I will pass it over to Kleber to talk about global illumination.
Hi, my name is Clever Garcia. I'm a principal graphics software engineer working on the Frostbite engine. And today I'm going to talk about the global illumination solutions that we developed for Dragon Age the Veilguard. I will start by sharing some of the global illumination results. We can appreciate here that the environments were pretty radically different, from very rich outdoors, tons of vegetation, to very much flat architecture with tons of crevices and detail. There's also a lot of volumetrics in the game, a lot of indirect lighting coming in from many sources, from emissives. These are some screenshots of pre-production, some of the assets without the texturing or proper albedo with a placeholder, so you can appreciate more the irradiance. And these were some of the early results we were able to hit in pre-production as well, to build confidence on our GI solution. And then lastly but not least, just showing some of the areas that were light map versus not light map, and some of the decisions which I will talk about later as to why we pick some areas to, or some elements in the scene to be light mapped. This is also some other levels with tons of emissive geometry, casting irradiance in the scene, and tons of volumetrics from the lights and so on. So, what were our constraints? Originally, it was a team of 15 people when a 16 by 16 kilometer levels with huge variability. This project came in right around the time where Need for Speed Heat was ending, so we kind of picked up some of the technology that we had there, and we were trying to reuse it since we are an engine, and that's our job, is to effectively build solutions that can work across multiple games. Unfortunately, at the time, real-time ray tracing was still in its infancy, especially BVH and building, and ray tracing cost and reconstruction technology was not quite there yet. So we needed a faster global illumination solution in pre-production to be able to build confidence. So this was quite a bit of a challenge. We also wanted to limit the pre-computation capacity and the maintenance. So that meant that we were open to pre-computation, but we just wanted to keep that cost as low as possible. We also relied on to-place probes because we did not want artists to be authoring light maps for absolutely everything, nor placing probes manually. That would have been a big no-no, especially for the size of the team. We wanted to avoid light maps for that very reason. And another interesting property of BioWare games is that all the levels are very highly kit bashed. So that means that GI needs to be applied efficiently. If you use light maps in an extremely high kit bashed system, you're going to end up with a lot of instances. That means a lot of charts, reduced pixel density, per instance, which cannot be a good thing sometimes. We also wanted quick iteration, so there was a lot of emphasis on optimizing the path tracing results and the network calls and all that stuff, and how we sent data to be able to achieve fast bake times. And we obviously wanted to maintain very high quality as much as we could. So we just threw memory at the problem. We allocated around 500 megabytes of budget and relied heavily on a free streaming system. We also had levels which didn't require zone streaming. So we actually did not use a zone stream system for this. It was all free streamed. So as much as the level preloaded as possible, but the probe system would ultimately be working on a very high density streaming window. The collaboration was super fun. It was effectively me and Ben just chatting up in Slack and just throwing art and code at each other. From the engineering side, I was working mostly in two branches, reporting fixes, giving Ben optimizations, and then using the game team branch to validate. So that was the most difficult part, just keeping the two branches. But by doing that, I was constantly dogfooding, and I was effectively failing as fast as I could. I was discovering issues left and right, which allowed me to harden the system as much as possible. I also iterated vertically, so that means I wrote for the initial implementation everything all the way from the UX, the editor, all the way down to the pixel shader and like the deferred passes and all that stuff at the beginning. Obviously, afterwards, we could do another React chat on that, honestly, but what happened after in post-production was also awesome. We had a lot of team members coming in, optimizing the stuff I wrote and taking it all the way to completion. So you can see also me and Ben just being excited about some of the optimizations. This one was a fun one. This was like a 6,000% improvement on just how we sent data over in our SNDBS bakes, which is basically by batching more, we got a huge gains and stuff. Now, I will break down Frostbite a little bit into the subsystems. So the first one is called Flux, and Flux is basically a suite of radiosity. What it does is that it does the probe placement itself, and it also does the radiosity baking, but it works as a DLL completely decoupled from the engine. It is headless, so that means that you can actually send pieces of the bake over the network, and then Flux will stitch them back together. Flux Viewer also is a standalone editor inside of this Flux DLL that allows you to inspect and see any issues in the bakes or any artifacts. The other part that we iterated on was GA Grid, which is the probe placement solution for streaming. So this is the Frostbite cook pipeline and also the runtime system, as well as the UI widgets for the editor. The runtime is basically fully probe lit, streamable volumetric probe system. The cook pipeline is async bake calling Flux, and it generates game ready assets. The bake times, we were able to reduce them all the way down to 10 minutes to 15 minutes per level at the highest quality. So if you chose a lesser quality, the bakes were usually done at like a 2 or 3 minutes. And even better, you could actually bake zones separately. So that means that you can achieve higher bake times. There were also very few light maps, mostly out of place probes. The final results of the baking looked like this. This was kind of like our eureka moment. This specific asset. Ben sent this to me and I was very, very excited to see it. This is around 500 megabytes of streaming budget, which is what the Dragon Age ended up shipping with. We did as much as possible in probes, and the placement was really, really dense. It was almost like a point cloud in the game, especially in the areas that were the highest detail. Light leaking, well, what we did is we built chunky levels as much as possible, with the thinnest wall being 0.5 meter wide. So keeping everything around 0.5 meter to minimize leaking. We also had this conflict between light maps and probes. We kept the entire rendering code path for light maps, still using light maps since they are unbeatable when it comes down to certain pieces of geometries. Like in this example, you can see the little hat-looking rooftop that is light map. And some of the pieces of the architecture, we effectively chose to use light maps for the most problematic ones. So the cool thing is that Flux is able to bake light maps and probes independently within the same scene, so you actually get the same results of the bake of irradiance. Now, when it comes down to the details of the actual probe grid and the probe tree, I'm not going to cover that in this talk because this is not really a graphics talk. This is more of it is a graphics talk, but it's more about the architecture. So I will leave the technical details or the algorithmic details of the probe grid on this presentation, which we did a few years ago. It covers pretty much the same data that we utilize in NFS, but it's obviously missing all these architectural pieces. Hence why this presentation is here. So for more details, we can see how the probe grid is built and utilized and sampled from this talk. The baking process looked a little bit like this. The artist comes in, opens Frostbite, clicks on a button, and then immediately it builds a Flux scene. That process is really quick. It just walks the entities, catches everything that casts GI, and then builds a custom scene representation that is sent to the plugin of Flux. Flux then divides the work. It actually duplicates the scene data across the workers, but it only does it on area. So effectively, each area of the game, which we call a cell, will have a little bit of the neighbor area as well, so we can have proper stitching. All these areas are then stitched together once we get the results back from the network by Flux DLL, and then that generates the final bake results, which is the probe grid and then the light maps. Now this is interesting because SNDBS was effectively the solution to go out of the blue. So the previous vendor, we had a vendor, I cannot say the name, but decided to increase the prices. That obviously caused a lot of ruckus in the company. So we decided to switch really quick to SNDBS, which is a free solution if you're a PlayStation developer. And it worked extremely well. It was a little bit challenging to set up because the configuration is kind of complex, but props to Matti Hietanen, who basically pulled this off in a week and was able to put it together. We obviously iterated. We had tons of bugs, tons of caching issues, but I mean, we were able to solve them through the spirit of dogfooding and working closely with Ben. All these issues were caught very early on. VPN COVID was also a huge issue. At the time when people started working from home, the bake times would take just too long. So what Ben did with his team was to ask people to keep their computers in the office. That way they wouldn't have to go through VPN and the bake times would be still pretty decent. Flux also provides debugging tool, which is the Flux viewer, and this allows you to inspect things like QNAN normals and or normals that are zero at interpolation point, like if you have like two flipped normals in a triangle. And there were other issues that like it allowed us to catch really quick by just looking at the area where the artifacts were happening. So the tooling was very important to catch these and to have just clean bakes. Volumetric fog support was also kind of organic. It was very easy because once you have a probe grid, you just have to sample the first SH, and then that gives you really beautiful GI. Now, I want to talk a little bit about the sky visibility problem because this is a self-inflicted wound. So what happens is originally when you sample irradiance either from light maps or the original CPU probe system, is that you do it at gbuffer laydown. At least Frostbite does it at gbuffer laydown, and then this goes into the gbuffers, into a gbuffer that holds irradiance and skyvis, and then it gets resolved in deferred lighting. With the GPU probe system, we basically added a way of doing it deferredly. So that is, after gbuffer laydown, there's like a little lighting pass that happens here, a set of pixel and compute shaders that do the deferred pass and apply GI. They patch the irradiance buffer on the pixels that are tagged to be probe lit. And then sky visibility also gets pinpoint here. But here's the problem, that it turns out that some users need to use weathering effects like sky visibility in the G buffer laydown. And these weather effects do things like covering, areas from rain and things like that. So sky visibility is very, very useful for that. So what do? Do you sample the ProGrid directly from here? And that was a big problem because this is very costly. This effectively makes all the shaders that take rain really, really expensive because they have to tap the ProGrid here to get SkyVis and then later apply the patch defer pass. So how do we fix this? We build a presample world 3D cascade, which is just a very simple box around the camera, set of cascades. We sample the ProGrid in world space every time the camera moves. And then the G-buffer laydown just has to do one single tap on a 3D texture, which was more efficient. This solved the problem, kept the VGPR count of the G-buffer laydown low, and it was really nice. Here's an image of what that looks like. You can see the cascades here in the editor around a camera point. And then on the left, how sky visibility was tapped. So it gave us really, really nice results. The visuals were different, obviously, from sampling the probe tree directly, but we don't want to do that. It's too expensive. So really the visuals didn't change as much. Other issues that we were fixing constantly were light leaks and mostly determinism issues between the bakes. It's very important when you bake to keep the bake deterministic because when you're in different agents and you're stitching back the cells, you want to make sure that the GI matches those edges. So these were a pain in the butt to fix, but we got almost all of them. So you might see a few seams here and there in the final game, but for the most part, the seams were all fixed. And then we also exposed for content creators a few tools like content creators were able to tune the level heaps directly for the GPU ProGrid. We also exposed streaming warnings, so effectively some areas of the game failed to stream due to out of memory. This actually told the content creator where to go and maybe decrease resolution on some of the assets. This ends the portion of my presentation, and now we'll defer to Darren Stewart, who will talk about reflections.
Hello. My name is Darren Stewart, and I'm a senior graphics engineer in the Frostbite rendering team with a focus on ray tracing. Today I will be presenting some of the work we did for ray traced reflections in Dragon Age. To start with, I'd like to mention that Dragon Age is not the first EA title to ship with ray tracing, so we were building off of the great work on previous titles. Battlefield 5 was the first Frostbite title to ship with ray traced reflections, and the Dragon Age implementation built upon that. DICE presented their Ray Traced Reflections talk in 2019, and much of the core algorithm from that talk still remains. After Battlefield shipped, the Frostbite ray tracing team spent some time developing a new cross-platform ray tracing framework. This was presented in 2021. And finally, developed as a partnership between Seed and Frostbite, we have our Ray Traced GI solution. While the GI solution and Reflections don't share much shader code, we do share a lot of the general framework for managing acceleration structures and shader bindings. Before we get into the Dragon Age changes, let me just give a really quick recap of how reflections worked on Battlefield 5. To start with, ray traced reflections within Frostbite are designed to be a drop-in replacement for SSR. Just choose which type of reflections you want, pure SSR or ray traced. With both algorithms, first we do G-buffered laydown like any deferred renderer, then we decide where to apply reflections on the screen. We do some ray tracing and denoising, and finally, during deferred lighting, we combine the results with other light sources. Of course, the ray tracing part of this is a little bit more involved, so let's break that down further. For tracing through opaque geometry, we separate the opaque trace and the material evaluation from the lighting computations. This is analogous to screen space deferred lighting, where we collect material information in a separate G-buffer and then follow up with a separate lighting pass. The number and types of light hitting an intersection point is decoupled from the trace and material evaluation. Note that when tracing through transparent geometry, we do have to evaluate lighting inside the trace itself due to how the order-independent transparency blend algorithm works. Again, this is somewhat analogous to forward-rendered transparency with raster algorithms. Finally, we combine the results of the opaque and transparent traces and denoise the image. Of course, we can improve this a bit to squeeze out more performance. First, we note that for rougher areas of the screen, we can accept a bit more noise and shoot less rays. We just let the denoiser blur it all. For really rough surfaces, we won't allocate rays at all and just fall back to more traditional cube maps. So the variable rate allocation passes will break the screen up into tiles and allocate rays according to a fixed budget. Second, we can sort our rays into bins based on ray direction. This gives a little better coherency. And third, before we even bother with shooting expensive hardware rays at all, let's just see if we can find intersections using a screen space march. For a more detailed description of all these passes, I refer you back to the excellent presentation from DICE. So this is our starting point as we head into Dragon Age development, but there are some issues to address. First, the Battlefield 5 implementation was built on a forked version of the engine and was PC only. For Dragon Age, we needed to modernize the code and make it cross-platform. I won't bore you with the details here because it's quite engine-specific and frankly not that interesting. But even though the work isn't particularly exciting, I did want to call it out as being quite time-consuming. So instead of working to improve the algorithm, a lot of time was spent making it cross-platform and updating it to work with the newer version of the engine. Another limitation was that we had no checkerboard support. As it turns out, Dragon Age ended up not using checkerboard anyway, but that decision wasn't made until late in the development cycle, and so we had to update the reflections code to support it anyway. As Kleber mentioned in the GI portion of this talk, there were limited art and engineering resources, and this applied to ray tracing as well. The TechArt team didn't have a lot of bandwidth to create simplified shaders for ray tracing. World-building workflows relied heavily on kit bashing things together, which is really not friendly to ray tracing, and to further complicate things, a lot of the environment was outsourced, and the outsourcers did most of their initial modeling without ray tracing in mind. By the time we realized some artwork should be optimized for ray tracing, we only had a skeleton crew of environment artists that just didn't have the time. Basically, all of the best practices for world building just weren't practical when up against a packed production cycle. Next, the original denoiser from Battlefield 5 was ported to consoles, but didn't perform well, so we decided to switch that out for one based on SVGF. I'll talk more about that later. Another thing we knew we needed to address was that we had been evaluating artist-driven shader graphs and closest hit shaders. This worked okay on high-end PCs with really powerful graphics cards, but it wasn't going to cut it on consoles. And finally, we needed to add support for participating media volumes. These fog volumes were a huge part of setting the mood in Dragon Age, and so we needed to make sure that ray tracing supported them as well. So knowing we had a lot of challenges ahead of us and limited resources to tackle those challenges, we made some key strategic decisions really early on. Dragon Age supports both the 60 FPS performance mode and a 30 FPS fidelity mode. We decided early on that we wouldn't even attempt ray tracing at 60 FPS on consoles. With content not designed for it and not enough engineers to optimize for it, we knew 60 FPS with ray tracing would be unrealistic. But at 30 FPS in fidelity mode, we could be a little bit more relaxed. We also made the decision that we'd only attempt one ray tracing feature active at any given time, at least on consoles. We aren't set up to share ray results between different ray tracing algorithms, and each algorithm has its own LOD bias and culling settings, which also makes it difficult to share acceleration structures. So we advise the lighting artist, pick your poison. To assist with this, we set up controls in our visual environment system for turning ray tracing features on and off. The visual environment system in Frostbite is how artists can configure various graphics features like post effects, height fog, physical sky rendering, shadow maps, etc. These visual environments can be assigned to a level associated with trigger volumes or modified via schematics. In this way, the artists have complete flexibility. As it turns out, the artists preferred enabling ray tracing features on a per level granularity, which actually worked out well. By turning features on and off during level transitions, most of the related performance spikes are hidden behind a loading screen. And finally, for consoles, we thought running reflections in a half-resolution mode might be useful. SSR already had this feature, which had been used in previous titles and previous consoles, and we figured we should have it in our back pocket for ray tracing as well. When it came to PC, we decided to relax things a bit. If you have a newer video card, then you can turn everything on. If you have a slightly older video card, then maybe your experience is closer to the console experience. And if you have a really old video card, then just turn ray tracing off. But the user is given more options to decide for themselves. Earlier, I mentioned that Battlefield 5 did opaque material evaluation and closest hit shaders. We anticipated that this approach wasn't going to work on consoles. So as part of modernizing the algorithm, we immediately changed tactics. Using hard-coded shaders for material evaluation wasn't an option. We just relied too much on art-driven shader graphs with no practical way to convert those to generic hard-coded shaders. Another thing that was off the table would be any kind of material baking process like virtual texturing. It's an interesting idea, but we're just not set up for that kind of virtual texture pipeline, and attempting it would have been too risky. So our solution is inspired by visibility buffers. To start with, we do a screen march, which is the same as before. If we detect an intersection in screen space, we just copy the existing gbuffer data into our ray tracing material data. If the screen space march can't figure out if there's a hit or not, for example if the ray goes off screen or if it goes behind an object, then we continue on with the hardware trace. In our new version, purely opaque geometry goes into its own top-level acceleration structure, and we can use a very simple hard-coded closest hit shader that just records little information about the hit. We then follow up with the trace against alpha-tested geometry, which will use any hit shaders for alpha testing, but we assume that there are a lot fewer alpha-tested objects in the world. As a small optimization, if we detect a hit in the opaque trace, then we can shorten the ray for the alpha test trace. Then we do material evaluation using compute shaders with indirect dispatch. This will produce material information that gets packed into a similar format that our screen space gbuffer layout would use. Check out the bonus slides at the end of this presentation for a little more detail on how this works. Finally, we can combine the ray trace material data with our lights and produce a final color. This part is analogous to deferred lighting in screen space, except we operate on ray intersection points rather than screen space pixels. Let's take a closer look at the material evaluation. The way this works is that we mimic the raster pipeline, except we smash all the stages together into one hit shader or compute shader. The input assembler stage unpacks vertices from one or more streams. The vertex shader portion runs 3 times, once for each corner of the intersected triangle. The rasterization stage is replaced by barycentric interpolation. The pixel shader stage runs for the intersection point, and then the results are written out. This approach means we can use the same code generation pipelines that we already use for raster, just by changing the vertex and pixel shader entry points a little bit. This works well from a visual correctness standpoint, but it turns out that a naive mapping of vertex interpolators to barycentric interpolation can be really bad for performance. Let's take a closer look with a simple example to illustrate the issue. The first part of this process is unpacking vertices. This is pretty simple and not too bad, but note that we're allocating some registers for the vertex data. Next up, our interpolation function first runs the vertex shader 3 times, and those results need to be kept in registers. So that this contrived example, we use 14 registers per vertex because that's how many interpolators we used in our raster path. Plus, we're doing skinning and UV animation, so expect some additional temp registers. By the time we've gotten around to doing barycentric interpolation, we now have a minimum of 42 registers needed, but the high water mark will actually be much higher because we also needed those temp registers for skinning and UV animation. So expect occupancy to be quite low. Of course, the compiler can try to optimize this for you, so maybe 42 registers is an exaggeration, right? Well, sort of, yes and no. The reality is that the pixel shading portion that comes right after barycentric interpolation will likely use those results at the same time, or close to the same time. So the compiler is a bit hamstrung by those dependencies. So here's an example worst case scenario that we actually had to solve for Dragon Age. This particle effect shader had all of this data running through vertex interpolators. This particular shader was authored many moons ago, long before ray tracing was ever considered. Because the concern for VFX is usually on the fill rate side, the shader was authored to do as much work as it could on the vertex shader side instead, leaving the pixel shader to be quite simple. This works okay for regular rendering, but not so much for ray tracing. The shader maxed out all available registers, went over into Scratch, and then proceeded to max that out. I would like to say we came up with some clever ways to optimize this, but the truth is we were limited in time and resources. So we did the minimal amount of work to get to a shipping state. As mentioned before, we moved alpha-tested geometry into a separate trace. Even though alpha testing in any hit shaders can be expensive, we relied on it only being a small subset of the world. For complex shaders, we added a ray trace branch node into the graph. This allowed tech artists to provide alternate subgraphs. They could do things like skip detail maps or provide simpler versions of weather effects like raindrops or snow accumulation. We also provided a way to swap out alpha-tested materials for truly opaque materials. This is useful for when you have objects that aren't really alpha-test or transparent, but use stippling tricks to temporarily turn transparent when the camera starts to intersect, so as not to block the third-person camera view. The main use case in Offender for transparency was VFX. Dragon Age used a mixture of 2 different VFX systems. The older VFX system, called emitter stack, is where that worst case example came from. Particle simulation happens on the CPU, and artists are a little limited in what they can do, but we had a lot of content already authored in this older system. The fix for emitter stacks was to just create a ray tracing specific version of the shader graph code generation, moving almost everything from the vertex shader stage to the pixel shader stage. The newer VFX system, referred to as emitter graphs, keeps more of the particle work on the GPU. For this newer system, we had a compute shader that would write out all of the vertex data into a separate buffer. So rather than doing any real work in the vertex stage, all we had to do was unpack the cache data and then run interpolation. And in this more modern system, most of the lighting work is computed per pixel, so once again the amount of data we had to interpolate was minimal. So we optimized to the point where Dragon Age could ship, but we can do better in the future. With the vertex data cache, we can do skinning or any type of vertex animation in a compute shader, and then reuse that data for all subsequent passes: gbuffer laydown, shadow maps, acceleration structure builds, or compute material evaluation. Additionally, for Dragon Age, we were using Frostbite's older shader graph system. Now that we've moved to a new shader graph system, it will be easier to explore shifting work between pre- and post-barycentric interpolation, which also means this is a good time to plug Simon Taylor's talk from the Advances course last year, where he goes into the new shader system a bit more. Next up, we have to add participating media support. In Frostbite, artists can place volumes in the world that are used for fog, smoke, dust clouds, or similar. These volumetrics were a critical part of Dragon Age's art style, and if they were missing in reflections, it would be quite noticeable. Luckily, the lighting artist said that with reflections, the volumetrics didn't have to be perfect. We could take a few liberties as long as the bit of the fog color came through. So we traced through volumes from the reflection point to the secondary hit. At first blush, you might think to use hardware ray tracing for this, but acceleration structures and hardware tracing are actually overkill because we have very few volumes active. So just do a brute force search. In my first attempt, I tried to use math and analytical integration to calculate the physically correct contributions of each volume, absorption, scattering, and emission. Just find where the intersection points are and integrate back to front. I'll leave the math to the reader, but as long as the participating media volume has consistent density throughout, it's a rather straightforward integration. This worked great when prototyping the algorithm in a small test level, but failed when tested in game. The volumes can have a fall-off function to avoid having hard edges. In my small prototype, I just ignore the fall-off and it wasn't too noticeable. But with real game content, the volumes can be quite large and the fall-off discrepancy was too noticeable. Further, the fall-off functions couldn't be integrated analytically. The math just didn't work. I think we can do better here, either by providing fall-off functions that can be integrated analytically or by some other clever tricks. But given the limited development time, I opted for the quick and easy brute force approach instead. Ray march and grab samples along the path. Is it clever? No. But does it work? Yes. Does it perform well? Maybe. It really depends on how many volumes you support and how many ray march steps you're willing to use. For Dragon Age, we got away with a simple solution, but I suspect we will need to improve things for future games, both for performance and visual quality. Finally, we have to denoise the results. The original Battlefield 5 denoiser was ported to consoles, and while it looked pretty good visually, the performance wasn't great. After Battlefield 5 had shipped, there had been more denoiser research, and SVGF seemed to be in vogue. We could try using an off-the-shelf denoiser, but we have a problem. We can't use those off-the-shelf denoisers without some modifications to deal with our variable rate allocation scheme. First, the screen is full of holes where we've done sparse tracing. We need some sort of hole filling. Second, we may have large portions of the screen that don't have reflections at all, and wouldn't it be a waste of time to denoise empty tiles? So what we settled on was our own denoiser that takes inspiration from NVIDIA's Relax denoiser, but with our own implementation and some key differences for our use case. The first difference is the ability to operate on screen tiles using indirect dispatch, so we can skip over parts of the screen that don't have reflections. Next, we added a ray reuse pass at the start of denoising. This pass effectively does hole filling for our variable rate allocation. Another difference from Relax is that we opted to simplify the temporal accumulation pass a bit, taking fewer samples. This was a performance versus quality trade-off, and we erred on the side of performance. As for disocclusion, we didn't attempt anything fancy. Just lose the temporal accumulation when there's disocclusion and rely on results from the current frame. And finally, something new is the addition of a reactive mask. This allows us to mask out portions of the screen where the rays would trace through fast-moving particle effects, which would lead to ghosting. So this ends my portion of the presentation. Next, I will toss it over to Navi to talk about characters.
Thank you, Darren. Hello, everybody. My name is Navjot Garg, and I was the rendering lead on Dragon Age the Veilguard. Today, I will go through the character creator and appearance system that we developed for the game. In Character Creator, players get to choose between 4 lineages, starting with 16 base appearance choices. These are called presets, and players can do as many customizations as they want on top of these presets. Here are some examples of characters created in engine and in-game. As for our goals for Character Creator, we wanted to push the boundary on how many customizations can be done, and the characters should look the same in the game. We wanted to maintain our performance target and memory budget as per the constraints of different platforms. Our dev tool was created before in-game Character Creator, and we exposed only the most impactful subset of customizations to our players. Lastly, we wanted to reuse the system for infill characters as well, so that we could achieve enough variety in the crowds. This is the screenshot of our appearance editor, which was used by artists in Engine. The characters were divided into 2 presets, head and body preset, as shown on the left panel. The presets have multiple slots, but each slot can hold only one item at a time. On the right-hand side, there is a customizer panel, which allows us to apply these items, change shader values, and do other customizations. All the customizations can be broken down into 5 main things: the shader parameters, morph features, head blends, texture sets, and appearance items. We will go through all of these one by one. But before that, let us look at the character creator architecture in-game. The customization data is sent to Customization Manager from UI interaction, which breaks it into one of the 5 things mentioned in the previous slide, and sends them to Appearance System to apply to preview character. It also writes this to persistence, which is then used when loading main game or a saved game session. The appearance system is responsible for applying the various customizations. At pipeline stage, the preset is passed for all the items, which contains the mesh and material information, and cook them into asset bundles. These asset bundles are then sent to appearance component at runtime to instantiate the items and apply the shader parameter blocks. The shader parameter blocks are containers for shader parameters and values. These are stackable, and hence a character can have more than one shader parameter block applied to it. Shader parameters can be used to change things like skin tone, hair color, eye color, etc. The input is parameter name and its corresponding value. All the instances of shader parameter with this name in the character shaders are changed to this value. This allows for face and body skin tone, for example, to match. All the shader changes are applied using shader parameter blocks. There are 2 advantages for this. One, it is stackable and hence provides better management of shader parameters. And second, better performance because all the shader changes are applied at once. Next is morph features, which are used to change the facial features and body builds by mapping the weight range of -1 to 1 to a particular set of bone transforms. The input for this is facial feature ID for the bones to be transformed and corresponding weight. Next is head blends. These are different from feature morphs because it blends up to 3 head assets instead of individual bones. Input for this are the 3 heads and the corresponding weights. The blends are done using mesh compute and are computation heavy. Therefore, these are limited to heads only. Memory consumption was a problem for this because we have 4 lineages in the game and each lineage has 30 heads. So we only keep the asset bundles that are actually used in the character and avoid any duplicate loading. Texture sets are used for complexion, tattoos, makeup, paint, scars, etc. on face and body. These are memory heavy as well if they are not loaded or unloaded properly. So we use soft references to the assets that would help in loading and unloading texture asset bundles. The way this works is that we have data that stores texture paths, and then at pipeline stage, the table that has this data is passed and generate texture ID, which is a hash of path plus texture name. The texture bundles are then created to be used at runtime. These textures at runtime are loaded using the texture ID refs in the asset, and the appearance system applies these to the character. And the last one is appearance items. The appearance items contain mesh and material info, which can then be applied directly to the character. These items are loaded and unloaded asynchronously to get better performance. We can also apply new shader parameter blocks on top of the items, overriding the values that are provided in the shader information of the item itself. Now I will go through some of the takeaways from this development process. First of all, we started the development of character creator early. We started with dev tools to see what are the customizations that are most impactful and then expose only those in game. We refined the options and only use the high impact customizations. For example, nail polish options were abandoned and the effort required for jewelry to match the head body blend shapes was too much. Lastly, we keep an eye on performance and memory, and make adjustments as required. Strand hair in Dragon Age is a special feature that took a lot of effort, but it made our characters look awesome. This is the first time we did strand hair on such a huge scale and in a fantasy game. This feature garnered a lot of praise in gaming and tech community. Frostbite rendering team will probably do a more in-depth talk on this at some point, but I will go through some of the problems that we resolved while lighting strand hair in the game. First one was that we had a lot of different lighting environments and hair needed to look good in each one. Secondly, the lighter hair color tone was prone to unexpected changes. Thirdly, the hair lighting model was purely specular with no diffuse component. As a solution, we added fake character lights for consistency amongst different environments. We also made sure that at least one shadow casting light was present in the scene. LRV and sky sampling was a must for getting correct color. Transparency blending was also an issue with strand hair. So we did something called layer transparency, which is very much like transparent edge. We added an alpha cutoff to render the opaque and transparent parts based on that cutoff. The image on the slide shows the transparent portion of the hair in red. We also rendered the depth of the transparent part of the hair beforehand. It is used as a spatial barrier between transparent pixels that are under or on top of the strand hair. First, the opaque part of the strand hair is rendered. Then transparent objects are rendered, and we use transparent hair depth texture here. If the pixel is under the hair, it renders the hair. If the pixel is on top or equal to the hair, simply discard that pixel and render nothing. Then we draw the transparent hair, and finally, we draw the transparent object, thus layering the pixels of transparent objects on top of the hair properly. Another example of this in-game, the hair on the left image, you can see the opaque part being rendered and the transparent pixels being black. And then once the transparent parts are rendered, the final image is shown on the right side. To get proper transmission inside hair volume, we generate separate high-resolution shadow maps for strand hair called hero shadows. These hero shadows are generated for every strand hair object and the lights designated as important to the scene by artists. When applying shadows to the hair, we test to see if a shading point is in the hero shadows or the regular shadow map. The hair will not be in both, and therefore this is an optimization where we check regular shadow maps first, and if there is no hit, then we sample the strand hair hero shadows. Collider sets were used for collision between character hair and outfits to limit clipping. These colliders were authored with respect to the base models, but they can be customized since they can be moved based on the joint transforms. We had a rendering budget of 6.5 millisecond for a 33.3 millisecond frame and a 3 millisecond for 16.6 millisecond frame for strand hair. The hair sim took GPU compute time of around 2 milliseconds. This allowed us 8 strand hair assets at once on screen, each with 50,000 strands. Some of the optimizations and constraints we had to put in place to meet our rendering budget were as follows. Strand hair was only allowed on PC high and ultra settings and PS5 and Xbox. They were only used for head hair and beards, eyelashes and eyebrows being such small assets used card hair. Only the named NPCs in the narrative, besides the player character, had strand hair. All the crowd, for example, used card hair. We bundled strand hair and card hair separately to save a lot of memory issues, especially on consoles. The hair resolution was also adjusted based on upsampler and DRS settings. We disabled hair sim when the hair was off screen or far away from camera using sim logs. We also decimated render strand to gain more performance based on camera distance. Next, I want to talk about the shader variation system. This system was used for damage over time effects like poison, burn, freeze, etc. on player and NPCs. They were built to utilize shader parameter blocks because they are stackable. It also helped us avoid any SRV limitations on the hardware and the shader permutation bloat. This was also useful for showing progressive states of character, for example, injury and blighted states. It also helped us in managing content. So instead of maintaining several characters and invoking them based on gameplay conditions, we could just trigger the variation to be applied on the same template asset, and it can be removed from the timeline itself as well. Like I mentioned before, infill characters also use appearance system to produce varied character appearances on the fly. The data for these characters are stored in a data asset, and at pipeline stage, proper key value pairs are made based on the priorities set for each region of infill characters. These keys are used to load asset bundles. The database can be used to dictate all the game load constraints as well. For example, Elvish lineage characters cannot have beards. So while baking characters beforehand was an option, it wasn't as useful because it still required the presets to be created and kept on disk. We prioritized saving disk space by doing it on the fly and ensured appearances based on seed pool. In return, we had to do some more trade-offs. We had to use only 2 head blends instead of 3 as we would do in a full NPC like a player character. We also had to stop blending competitions at long camera distances. No feature morphs were used because the camera never gets as close to the infill characters. Infill characters only had card hair. The strand hair were not used for infill characters. The shader parameter subset was used. For example, no makeup was used for infill characters. Similarly, texture set subset was used for complexion. One MIP offset for all textures on platforms with memory constraints like Xbox Series S was used. We did not make any separate low poly models because LODs were usually good enough for reducing the geocomplexity at that distance from camera. The division of data by region allowed us to load and unload assets as needed for that region, also provided better content management for artists. So as you can see from this screenshot, the infill characters in the distance are varied and they produce proper results. We had characters ranging from different lineages, wearing different clothes, and having different kind of appearance items applied to them. So that's the end of our presentation. I hope you all enjoyed it. I want to thank the graphics team at BioWare who worked very hard to successfully ship this game at desired performance and quality. And I would also like to thank the Frostbite rendering team who supported us every step of the way in developing this visually stunning game. Lastly, I want to thank our speakers for presenting today and the conference organizers for making this interaction possible. Now we go to Q&A.
And we are back for our live Q&A. I'm joined here by Navi, Kleber, and Philippe, who is going to step in for Darren, who couldn't be here today for the Q&A session. Philippe is a Frostbite rendering engineer working with the ray tracing team. Prior to joining Frostbite, he worked at DICE in the rendering team and also worked at Crytek and CryEngine in visual effects. All right, let's go. And Michael backstage helpfully arranged all the questions into categories for the speakers. I'll do this, like I'll read a few from each of the 3 kind of sections, and then we'll rinse and repeat until we run out of time. And for the rest, as usual, the speakers will hang around in Discord to chat after the live. All right, let's get it on the road. So, couple of questions from the global illumination section. First one, Volkan Ibelli. The question is, for Flux workers, why you separate executables and not threads from a single executable?
Thank you, Volkan. So it's a bit. There's a bit of historical context. Flux was created back in 2016 by Yuri O'Donnell, who started in the Frostbite team. And back in the day, the CPUs were not as powerful as a Threadripper that we can have now, which are like I don't know, 15 times more in terms of scalability. Don't quote me on that number. I'm making it up as I speak. So there's that historical context. So this started all the way back with Battlefront, and then the requirement, like you couldn't effectively like a bake on a Star Wars Battlefront level with just a single CPU would have taken hours because Flux is brute force. It's a brute force path tracer. So naturally, the solution was to distribute it. And in order to distribute it, you need to have a separate process with this old sandbox, and you have to distribute this amongst multiple computers and do the bake. The same was true all the way down to pre-production in Dragon Age. So this is why we chose that. Now, Flux can run locally as well. So you actually have a checkbox if you want to run the whole bake locally in your machine, or if you want to distribute it. And you know, the farm just happened naturally. So I hope that answers the question.
That was very exhaustive. Thank you. Next question from Tianning, still about GI. What do you mean by the 500 megabytes streaming budget? Is that the maximum pool size from streaming GI data at runtime into VMM from disk, or is that about streaming from the network solution you mentioned?
No, so the 500 megabyte limit is runtime Atlas volume texture data. So it's uncompressed spherical harmonic 3D texture. We have a 3D texture Atlas that has all the bricks and the components of the probe tree. And effectively, you allocate once, and then what you do is at runtime, when you're moving the camera around, as you see areas of the game, these pieces will be then moved from disk into this runtime 3D Atlas. And then that's the budget. So effectively, you can bake as many probes as you want, but the runtime will try to just to fit in 500 megabytes worth of that data. So I hope that answers the question.
Very cool. Okay, I'll get just one more from the GI and then we'll rotate. And this is the most popular question. So really like there are three similar ones that we can wrap in one. You already know what is it going to be. Would the light seams be fixed manually, maybe running a bake that contains the seam, or is there another way to fix it? People in general, I think, are curious about mixing probe and light map. How do you deal with the seams there? Seams are a huge problem in all scenarios, and your solution is also a little bit more complicated because of the two different techniques.
Yeah. So for light maps, it's quite straightforward. There's actually a paper. I can find out and post it on the chat, but there's a paper where you can set a system of linear equations between the seam of the textiles, and then you can effectively solve this with a linear equation. That's how we do it for light maps. For the GI grid or the Pro grid, is a little bit different because in the Pro grid, what we do is we have to duplicate the walls between the cells. So the primary mechanism is to duplicate the probes at that cell front. So effectively, that's why I mentioned determinism. If I run a bake on machine A and a bake on machine C, there are different areas of the game. We have to make sure that the outcome, the output of that bake is actually deterministic on those areas. So if you have non-determinism, it's possible that some rays might fall into like back faces or hit too much of back faces. But we still had some seams that were caused also by bat geometry. So just triangles on top of triangles and then rays getting stuck there. There's a whole talk on that I can post as well of how, like more of these specific examples. But yeah, stitching is like also like a big topic. Yeah.
Thank you. I'm sure that in Discord there will be more. And by the way, I love the T-shirt with the old school EA logo. All right, let's cover a couple from ray tracing. Ilias asks, what particle effects were so slow in DA compared to other particle-heavy games like Battlefield?
So I can take that one. So that was mostly combat abilities. So those are the most expensive ones, specifically because of the sheer number of them that were going off on the screen during combat. So yeah, those were the main ones which were more expensive, and they were kind of a mix of the the two systems that were mentioned in the slides and the presentation. So the legacy system and the GPU based system. So there were like two systems running during that time.
Makes lots of sense. From Lai, you mentioned calculating skinning in the heat shader. How you build blasts without caching pre-computing the animated geometries?
Right, take this one. So what Darren mentioned there was the skinning for that it was necessary for shading. We do have compute shaders to pre-calculate the vertex positions into SRVs, so then it can be used for blast updates and builds. Yeah, so we actually do both. Yeah, but that compute shader just calculates positions only for the blast builds.
Okay, thank you for the clarification. Another question here on the volumetrics. Does the engine handle actual heterogeneous volumes or just homogeneous with a follow function?
So yeah, I can probably answer that one. So we have participating media volumes, and you can stitch a texture, 3D texture inside of them. So I guess this would qualify them. Correct me if I'm wrong, but I guess this would qualify them as heterogeneous. So that means that you can have like a cloud or a representation like that. And I think that's what the question is referring. In the talk, we mentioned how we integrate them, and we're actually gray marching them. So there's no analytical integration. You actually have to shoot array and then just march a certain distance and numerically integrate. I hope that answers the question.
And I think the volumes could be nested, right?
Correct. Yes, the volumes can be nested, free transformed, rotated. They don't have to be axis aligned.
Perfect. Okay, let's do another one here. A question from Malek. There are lots of semi-transparent objects in the game. Previously, you mentioned that any heat shader are run for alpha-tested objects. Does that mean you render transparent objects as dual-sided materials? If so, do you handle front and back sides differently, or you have like code for refraction, stuff like that?
All right, so first of all, we don't have refraction, so we don't need to do that. For semi-transparent objects, yeah, Nara would Darren will know better about this, but I'm assuming that it's probably similar to what Battlefield did, and that was we will use any hit shaders to do weighted blend, so it's not quite or independent transparency, but it's kind of similar. At least that's what we do in particles. Particles are done that way. Translucent objects, I believe they're done the same way as well. Yeah.
Interesting.
I hope that that answers the question.
Very interesting. Let's move to a couple of questions on the character creator. Eliseo asks, did they have any funny bug when determining the mix of faces or the morphological modification? And if so, how they did solve it?
So we did have some cases where for the feature morphs, we did have some cases where like some of the ranges would result in either like exposing say teeth out of the mouth and all that kind of scenario. So the way we fixed it was on our transform side. We have this evaluation functions. So every feature ID was corresponding to however like -1 to 1 mapping, however that was mapped to the transforms for those particular bones, and we could control like how much that mapping could be. So we put constraints on that, and that's how we managed to reduce that kind of occurrence. Still, it is very much possible to maybe make like an ugly looking, funny looking character. So that's definitely possible.
Very cool. A question from Lai. Would like to know the typical strand counts for characters for 6.5 millisecond, 3 millisecond cases, if possible.
Yeah, so we usually had the same limit for the number of strand counts, strand hair count. So it was 50,000 strands for each asset. The way we tackled this on the rendering side was we had this rendered to strand hair ratio. So for example, if we say had even more strand outs at author time. So for example, say artists made some hairstyles which required at least like 60 to 80,000 strands, they were able to put in a ratio that would at render time reduce it to the required limit. And then uh, for the different modes, the 6.5 and 3.3, for those we did not actually change the strand hair count limit. We instead, most of that was we were able to render without changing the strand count limit, and only taking into factor what was the resolution that this was being rendered at.
Thank you. I think we're technically already out of time. Let me just choose a couple of questions, and then the rest, of course, like we will engage on Discord. Another question here that I personally like to ask. This is from Tian again. Can I get more detail on how the shader variation system avoided shader permutation bloat?
Yeah, basically, for the shader variation system, we were able to replace the shader that was in there with something that had, say, a poisonous effect or something on the character. So we didn't have to run that in the same over shader, and we didn't have to like write separate permutations for that. We did we were able to cut a few corners in the alternate or the shader that was to replace that one. And the alternate shaders would have, say, you can say like some build up for, say, rain shadows or something like that. Then that would just override the previous shader which was on that, and that's how we would reduce the permutation bloat, which would have happened if we had like permutations for, say, rain buildup. Yeah.
Thank you. Okay, I'll just take this one, which is just a very general contextual one. You mentioned you had only 15 people on content. Actually, I'm not sure if that was overall content or specific level art. That is also something that I'm curious about. But the question is, how many rendering engineers did you have?
So we had 5 rendering engineers on the BioWare team, and then we were supported by Frostbite rendering engineers on specific areas. So, but yeah, like 5 dedicated rendering engineers for the game itself. I also want to clarify that the 15 people on content were not for the whole project. They were like specifically for the level content.
Mhm.
And then we had like other artists. For example, for character, we had different artists, and so on.
Thank you. Okay, we are really out of time, so we will go into a short break. Thanks again for your generous availability in answering all the questions. I know that there will be more to come. We will go into a short break and see you back at the half-hour mark.
Thank you.
Bye.
Yeah. Right.